Structural analysis 2, real world method, an example, truss. Let's solve this example. So if we want to calculate the vertical displacement at joint B, so we have a truss consisting of three members, AC, BC, and AB. And we want to calculate the vertical climb down of joint B to effect of 150 pounds concentrated load which applies at B. So as you can easily see here, we do have a roller at B and a pin at C. So definitely we have a CX, CY, and for roller we just have AX. So if we want to, we can easily know that we have a force. We want to, in the entire structure, we have only one force of 150 applied at B, as you can see here. And at the same time, there is no other forces on the structure, and we want to calculate delta B vertical. So that's the situation. You can apply the real work method, and you have only one force on the entire structure, and you want to calculate the effect of displacement at the direction of your load. So let's see, if we want to make a moment about any arbitrary point on this structure, the best location for a start is C, because by choosing C we are eliminating two forces. So Cx and Cy are eliminated because of pin. And so if we just calculate the joint C, summation of moment about C goes 0, it just gives us AX times 6 minus 150 times 8. 150 times 8 goes 0, and it just gives us AX is equal to 200 pounds. So as soon as we know what AX is, we can simply jump to the pin at A and the roller at A, or joint at A. So AX is a 200 push to the joint A. Definitely that force should be cancelled out by FAB from this member. So if we project the component of X and Y component of AB, so this is 3, 4, 5, and it just simply says the horizontal component of FAB will cancel out AX, and also the vertical component of FAB, which is a downward push force, is cancelling FAC, which is the force on the member AC. So if we just, and at the same time we do know if a force like, for example, FAC pulls up the joint, it definitely pulls the member as well. So if any force pulling this joint, so definitely it just pulls the member as well. And at the same time for FAB, if any force pushing a joint, it just push the member as well. So FAB is a push member, compression member. That's a pull and side member. So by writing the equation of equilibrium, a 3/5 FAB, a vertical component is equal to FAC, and the horizontal component 4/5 of FAB, force at AB is equal to AX, which is 200. We already calculated that. Just simply says FAB is 250. We already know FAB is a push, so that's a negative 250. And the vertical component is also equal to FAC, and that's push. That's a pull, so that's a positive, and that's for 150. So as soon as we have these forces, we can simply jump to joint at C, there is only AX, which is 200, so it just says this is a 200 force in the other direction. So if any force pulls the joint at B, it just pulls the member, so that's a positive, that's a tensile member. As soon as we have all the components on our structure, we can create the table for forces and their length and also their internal forces. So as soon as you know, if we have an axial force and we apply a tensile force of N at the end, U internal energy. So internal energy is the work of internal energy, external energy. This is the work of external energy gradually stored in the structure and turns to an internal energy. So it means Ui is equal to U. So this is Ue external, and that is stored like a strain energy in the member. So and at the same time, from mechanics of solids, we do know delta to tensile load or just the compression load. A delta is PL over EA, either if it's horizontal or vertical member, doesn't matter. So by replacing P by N, because it's all force, and delta by delta, we can add up these two equations and get the internal energy like N squared L over 2A. So as soon as we have our original structure with the force projected on it, so we can have a U internal forces is summation of N squared or Fi squared L squared Fi squared times the length of the member over 2 E times area of that member. So if we just take the constant of 1 over 2EA out and forces of each member, for example, this member squared, if this is 6, if this is 8, this is 6, this is 10. So that's L for that member, and then 150 squared times 6, which is the length of the member, and then 200 for FBC, which is positive 200 squared times the length, which is again 8, like replacing in the equation. And as soon as we have that, a 100 times delta, original P was 150, can cancel out these two with each other and replace 150 here. And now the only unknown of our problem is delta B vertical. As soon as you replaced it in the equation, it just end up to be delta vertical at B 7,200 pound square times feet over EA. This is not the unit. If you replace the unit of EA over here, because it's just given to us like a parametric, and it just turns to be, for example, like, for example, 0.2 feet. The unit is either in SI is meter or millimeter or feet inches. It's kind of a small displacement in the structure. Thank you. We solve examples. Thank you.